Okay, this is the second session on challenge-based learning unit design. And so last time we specifically talked about the challenge-based learning process and what are the ways that one can implement that. It is, different people can do it slightly differently. The challenge-based learning process implementation can vary quite a lot depending on the challenge you're doing. Okay, can you very quickly tell me what are the essential elements in the challenge-based learning? Anyone?
Yes. Big idea.
Yes.
The essential questions.
Yes.
And then the guiding questions.
Essential questions and selecting one.
Yeah, then you go with
challenge,
the guiding questions.
and then the guiding questions. Okay. Very good. So today we will be talking about the engineering design process. This most probably will be quite natural to all of you, since most of you are exposed quite extensively to engineering. This is more of a prescribed process, not that much open. Okay, so we should be able to go through this fairly quickly. Okay, we'll start with an activity. There are two groups. Okay, let me go over very quickly over what you need to do. Use any of the materials that are kept on your table, which are described there. It's up to you to choose which you want to use, but do carefully make a note of what all is available to you. Okay. One team has two people, so you'll work as a team. I'll give you 20 minutes to do this exercise. What the design challenge posed to you is, you want to design and construct a device that either maximizes or minimizes energy transfer through it. Okay? And it's up to you to choose. Your deliverables are the device itself. Okay? Your model structure is your prototype structure, so you're not doing any scaling or anything. Do note down on one of the white pieces of paper whatever process and steps you're using. Okay? What ideas come to your mind, etc. Anything that is involved in solving this problem. Okay, all of you have done engineering design problems, so, and all of you know that you have to document your process in order for someone else to understand it also. So keep that in mind, wear your engineering hat to note down every detail. So you will produce, the deliverables are the device itself that you produce. Then from each team, what we would like is a verbal description of, in your own words, the statement of the problem, the design process or design cycles or design steps that you used. Document these, write these down, okay, so that you can do it, and why you chose that design. So whenever you choose a design, definitely you're choosing amongst different alternatives. So you always should present the different alternatives also, then justify, this is what I considered, and based on such and such reasons, we decided to go ahead and do this one. It may fail, that's fine, okay, because you're not completely going to be testing it. But I would want you to come up in your mind, how would your plans to test the efficiency, how well did it perform? What do you think will be the testing process for you? Okay? And a name of your device. So in the end, the groups will be presenting it. So decide amongst yourselves. You're the Lone Ranger, so you'll be the only one presenting. amongst yourself who will present what, because that will be a typical thing as part of this process. It is a teamwork. Okay. It is a team problem, so you have to be reporting as a team. And when we say reporting as a team, it automatically implies that each member of the team should be reporting certain aspect. And when reporting, it should be done in a systematic manner so that it should be clearly defined amongst yourself who will report what and when. Okay? So note these things down and plan that out. Okay, you have now 20 minutes to do this problem.
If you want the blank to start over here. Or I could just put it this way. This would be fine. We can go right to that, that works too. We want to this stuff.
Much time do we have left?
You have about 6 minutes more.
6 minutes, all right.
5 minutes more.
You get-
ready? Even if you have it incomplete, that's fine. You can explain.
Just.
Okay. Okay, I'll call this as team 1, and this is team 2. And I'll be asking specific questions from each team. And then we'll come to these. Team 1, what was your understanding of the problem?
Well, we addressed the problem that we want to minimize energy transfer from one side of the system to the next.
Okay. Can you be a little bit more explicit, externally or internally? How? If from inside the device to outside or reverse?
We want to minimize energy transfer going from, so if this is your device,
Yeah.
you're going to have energy coming in this way, and we want to have the least energy get out that way.
Okay, very good. Okay. So that is what you wanted to. Did you identify any, in order to be able to do the problem that you selected, what criteria would you consider, what constraints would you consider as far as your design is concerned?
Our own design?
Your own design? What you said that energy will, whatever energy is coming in, least amount will go out. Okay. What design constraints did you think will lead to accomplishing that goal? As far as you're designing your device is concerned.
Well, we're taking energy in from one direction and out in the exact same direction.
Okay.
So there wasn't different directions of energy coming in or out of the device.
Okay. Okay, very good. Team 2, what process did you use in brainstorming the arguments? You were 2 members. Was one person the primary person and the second person was a listener, or both of you contributed?
We kind of just shared what our ideas were at the beginning.
Okay.
And kind of adopted them.
Can you a little bit shed some light what ideas you considered?
We talked about like a domino, part of domino cards, how you move them and maybe from the beginning to the end, you know, that kind of motion. And so we decided to construct a little machine.
Yes.
So to maximize energy transfer. So from one end, just by a little application of force, we get to move, apply more force, more energy to move an object.
Okay.
Larger object.
Okay. So your energy has to do with motion in your case.
Well, yeah, transfer of
Motion.
this motion, this energy to this energy.
Okay. From
Yeah, it's more visible. We both kind of had ideas about maximizing energy transfer.
So yours is very, very different than theirs. So really, what you did was, the questions I posed to you in the very first phase of design is really you identify and define yourself, what the problem you're solving. You define it. And what you did is you sort of, after defining the problem, you gathered information and brainstormed how will you go about doing it. And in your case, you were looking at transfer of energy from one type of energy to another form of energy, which is perfectly fine. Again, I asked the team 2 one more question. In order to be able to do that, did you plan your investigation? Did you write down how would you go about, for example, what energy will be transformed to which energy first, and from then what to what energy second, third, like that? Did you plan your investigation?
Like written? No.
Yeah, but
we
even...
didn't write what kind of energy was going to
Yes.
transfer, but we were thinking about it. I only made one of the 3 that I came up with.
Okay,
She made about 1.5 of the
Okay.
2 or 3 that she was thinking about, but we planned what we're going to do.
Okay.
Just
So you, because in your case, you would have planned what type of energy you'll be transferring first,
Sure.
and second, and third,
yeah,
like that. Okay. So this is really what you did in your, where you're gathering all the information possible to be able to proceed with the problem. Now, team one, what alternatives did you consider?
What do you mean by alternatives?
In any design, you definitely must have considered a lot of different alternatives. Why did you choose this device only? Did you consider any other possibilities?
I guess, honestly speaking, no, but like we decided to change the spring system, you know.
Yeah, I guess we sort of went from our understanding of physics and engineering. So
Okay.
alternatives were considered, I guess, sort of previously in our minds type of
Okay.
thing. But we took our understanding and thought, what is the most efficient way to minimize energy transfer?
So
And
you
so,
did-
so we sort of already had those ideas,
Okay.
so we didn't really
So
consider
you did
other
consider
things.
pros and cons.
Yeah, yeah.
Okay.
And we had to, I guess, consider, yeah, we had to consider what to use
Okay.
in our
In the materials
one
you
materials, how to build the springs.
exactly. So one of the essential things which I was so in your alternatives, what you had available.
Yeah, yeah.
And you put it. So really, in any design cycle, then you always consider some alternative, whatever materials, what is possible to be done with that. And there could be number of different things. There, for example, in your spring systems, you could have changed the number of number of coils or whatever you want to, because the size of the paper length could have been changed to get more coils.
got it.
And
It worked.
okay. In a design cycle, the next thing is after you consider a lot of different alternatives, then you make a strategic decision. This is the one which appears to be most promising, and you'll try that. Okay? Before you start constructing, you should. So, team two, how did you go about selecting? This is what we do.
Well, like we said, we were thinking about dominoes. I thought that would be
Okay.
boring and tedious cutting work.
Okay.
And we figured, I was looking at the materials and it's all like we had 5 different cardboard squares, and I'm like, well, this could each be individual modules for
Yes.
Rube Goldberg.
Okay.
Actually, yeah. So the Rube Goldberg idea was mine after I looked at the materials, and it was like the materials led me to a solution.
Okay. Very good. So definitely in the design, you always then come at a strategic decision. This is the one we keep in mind. It's an open-ended problem, because in your problem also it could change depending what energy you'll first transfer into what energy, then second, and all. Your construction process could change quite a lot. Okay, team one. After you made a decision that this is what you start constructing, did you make a drawing of your?
Yeah, we start with the diagram first.
You started with the diagram. Okay,
And then
so you laid down. Did you? Yeah. So that's excellent. Okay. Yeah. Typically, in the engineering process, you always. Did you then, after doing that, how did you proceed after that?
the model is pretty, like we divided our parts, we gonna go with, like a model is composed of 1, 2, 3 parts. So we
Okay.
distribute them on ourselves and then we.
Okay, so you divided the total design into
Yeah.
distinct components,
Yeah.
and you started constructing each component separately and then combining the two. That is a very typical process, because the whole device will consist of different components. Okay, and so you have to. This is called the implementation of the solution. You cannot just randomly start it. You first lay down the process, and that this is what I'll do first. You said you deciphered it into different components, and then did that. Okay, so then you constructed your device. What about team 2?
Yeah, we drew a mini
Okay,
diagram of what it's actually. He did one component and I did one component, and basically I just, made a little sketch of, even though my sketch actually changed from what I constructed because I realized.
yes. So one thing I was going to ask is, you do plan something, but then it changes as you start implementing it, because you see, oh, you thought that this will work, and then this. Okay, now both the teams, can you explain your designs now?
So we were trying to minimize energy transfer from one side of the system to the next.
Okay.
So we used springs. We used a two-layer spring system. So the springs are going to compress and use up a bunch of that energy
Okay.
that comes in this side, so it won't go out that side. And then we also use this box here in the middle. This box is filled with balled up pieces of paper.
Okay.
So it sort of provides, the springs will compress faster and the box will compress slower. So it sort of provides a gradual compression of our system to maximize the use of energy. So the balled up piece of paper, the box will compress upon itself, squishing the balled up piece of paper and eliminating the airspace inside of there, just increasing the compression time.
Okay, very good. Team 2?
So this is design, and then we're trying to move this. We're assuming this is like a big, really huge mass of rock or whatever we need to move. And so we start from having a string with a boulder, maybe a little boulder here, and maybe at the press of a button, or maybe just with a little motion, it moves this static thing.
Okay.
Pushes this, and this pushes.
Okay. This and that moves
and
it.
then that moves it. Yeah. So it's just.
So you have a transfer of energy, and ultimately your objective was to move a big boulder, which otherwise manually could not have been moved.
Yeah.
That was your.
Have a bunch of potential energy here.
Yes.
And here, and transfer
So
that to kinetic, and
kinetic.
back from potential to kinetic again, and then.
Fantastic. Can you tell me a real-world application of this?
Well, this type of thing is used in the bumpers of cars, sort of, and airbags, shoes, type of.
Yes.
Your
Wherever
knees,
you want to protect
your knees and legs, they compress to lengthen the amount of time to reduce the force.
Exactly. So that the impact is not a sudden impact. Yours is basically, it's quite obvious. Your goal was to move that big rock boulder which you manually could have not moved. So really, you have to communicate ultimately this thing and also give some validity that it's a valid solution. If you were to redo it or to refine it, what would you do different?
Well, there could be different materials used. I mean, if we had access to other materials, we could research what materials would do best to compress
compressed.
at different rates.
So the efficiency could be
Efficiency can be increased.
So explore possibility of different materials,
Yeah.
which you could not do it because you were given some.
Yeah.
What about yours?
The materials certainly could,
Okay.
it could be
Would you
improved.
change it any design?
Well, we have about 2 things so far. We had at least 5 or 6 planned. So we could, with more time, we could expand it and make it.
So you can have more
larger.
moving devices
Yes.
in between?
Yes.
Okay. Could
If
you,
you're going to optimize the amount of, if you're going to optimize the amount of energy transfer, then having more modules in the system can certainly do that.
okay, very good. So really, this is what about the different elements of design. Let me very quickly, first of all, this same problem was given to a group of teachers. The same problem has been given to high school students, to district administrators. They thought of a completely different solution. Being engineers, you thought of transferring of forces. Okay? There they were looking at more of energy conservation, of actual energy, like a device such that if you keep something cool inside, it remains cool inside. If I put ice cubes inside, they do not melt for a certain, it had directly to do that. So really, this is something that one should be prepared for. Okay? This is a brilliant example because I think this had to do because of your prior knowledge. Okay? Being engineers, I think one of the main things is you design devices to operate something. And here you thought of, both the groups surprisingly thought of transferring of forces such that some efficiency could be improved. What name would you give to your device?
The spring stopper.
Spring stop. What about yours?
We were just going to call it some kind of generic root over number 1
Oh,
or something.
okay.
Lame.
I know.
Lame.
It's not spring stopper.
No, it's not. Yeah. Copyright.
So yeah, so definitely you'll give a name which shows the functionality of the device. This problem that I had envisioned of introducing was for actually transferring or storing energy or inside, not to go outside, or vice versa. That was one of the reasons none of you used the foil. If you were constructing that type of device, you would have to use a foil. Okay, that was very surprising that you didn't think about it. You use the foil, but for different purpose. But foil can be used very easily for reflecting or energy. If you're talking about sun rays, if you were going to heat something, it could be a very good source. So you'll put it on the outside, isn't it? So that it gets heated and then something inside could get cooked, like a solar heater type of a thing. So that was the reason for giving a foil. So it's a very open-ended problem. Suppose it was that energy thing, I would want to, because in none of the examples we talked that much about next generation science standards. If it was a device in which I was constructing device where energy had to be either maintained or had to be released, either one of them, and I'm talking about heat energy here, then there's look at your handout. There's one, for middle grade class students, there's a, look at F. Can any one of you read that out to me?
Says compare, evaluate, and design a device that maximizes and minimizes thermal energy transfer.
Yes.
Define the selection of materials used to construct the device.
Okay. So I did not purposely give that word thermal in your, I can bet with you if I would have thrown that, your whole design would have been you would have come. I really wanted to see, particularly since you were engineering students, would you think differently? And I'm not surprised that both the groups thought completely differently. But originally, that is what that, and I purposely removed the word thermal.
Totally changed the.
Yes, I removed. So what I was saying is, if you as a teacher want to teach something, you have to be very strategic in defining the challenge. Okay? This is a fantastic example, and you proved my point. I'm quite amazed that it happened that way. I was thinking that it will not happen.
Well, they're very advanced middle school students.
Yeah. So I used that, removed that word thermal there. But this is one of the standards that has to be addressed. And if you look at the left column, it completely goes with what you did. Isn't it? Look at that. Where you're talking about the science and engineering practices. Exactly, this is what you did. Okay? And look at the last column. These are the three-dimensional, two arms of the next generation. And the next one is cross-cutting concepts. And here also, if you look at it, you address these things in your design, isn't it? And then the middle part was basically content related. So here, so one thing message that you should have, when you're constructing, particularly for your undergraduate course, if you're going to be using this concept, design activity, be very careful. And so the guiding question that should have come should have had the word thermal as part. Otherwise, it can be, and that is what that standard that we were thinking of addressing. There's a separate standard on the engineering design, which is the next handout that has been given to you. Okay, now very quickly before we disperse, design-based learning is a pedagogical technique which is used both in science and engineering, but it is used a little bit differently. Okay? It is definitely in both, it's an open-ended problem. Okay? And always there will be some constraints that you will have, which you would like to, that the design have to be. There could be some trade-offs, permissible trade-offs, and some performance-related criteria that you evaluate your design against. Okay, whether it's good or bad, so that you can check the solution. In the engineering design process, the only thing is the steps are quite prescribed. Okay. Whereas if I would want you to look yourself, use of the word design for scientific inquiry. It's very different, you will find. So in the engineering design process, you first identified and defined the problem, which then you gathered information, then you brainstorm different alternatives, and then decided to start your constructing of one, okay? And so you selected your best solution that you decided to construct. Then you actually constructed it, so implemented the solution. And then, of course, you would have tested it to evaluate its performance. And then if its performance did not meet your objectives that you started with, then you would have refined it, gone through a repeat of a cycle, and finally communicate your design. So these are the basic steps. And in the handout, in the presentation, these are sort of defined. And I did go over these with you when I was asking you the questions. So the questions that I had phrased were really these, and you can go over this in your spare time. Okay? So brainstorm possible solutions. Then these are some of the strategies for the main thing is you should give equal opportunity to everyone. Like I posed the question, was it driven by one person, or did all of you contribute towards the design? So the teamwork, because the more and more you do, the better ideas will come. The key thing here is that you should not be sidetracked or completely blinded purely by your past experiences. Many times, very innovative designs occur by serendipity. When you think wildly, oh, is this possible? Okay? You are willing to try something out of the box. And that is what is most of the discoveries actually, if you look at many of the products that occur that way. Okay. So the main thing is brainstorming. The key thing is every team member should be given an opportunity, because one of the team members may come up with the most brilliant idea, which others may not even think about. Okay. So this is something that the teacher will have to facilitate that happens. Okay. And then I did ask you this, did you all try different alternatives? What was, before you decided to construct your device, did you look at different alternatives? Did you create a drawing for it? Okay? And did you figure out how will it work? And both the groups did that, okay, without me even telling. Then you selected and actually constructed the device. Then you implemented it, following the plan that you had done. Like this group said, we decided who will construct which part, and then each team member constructed distinct parts, and then you assembled the total thing together. Okay, then of course you didn't do this part, then you will evaluate the performance and refine it. Okay, and then you will communicate. This is the key thing is, if you're implementing in the engineering design process, you have to touch each one of these elements. You have to facilitate. You cannot jump different steps. So these are some of the web links that you can look at for engineering design. A lot of wonderful examples are given here. And as far as evaluation is concerned, as far as the student is concerned, what you have to document were the students engaged. Like for example, we said, was everyone contributing towards the design? When communicating the solution, did everyone participate in communicating the solution? Okay. Was everyone given the chance to express? And there are a lot of different strategies. For example, in a group you may say, okay, everyone first note down their own ideas on a piece of paper. Give 3 minutes to everyone. Then say, okay, each one presents in the team I'm talking about, why don't you present your idea? If anyone has a new one, has to add to it, then add. And then brainstorm that, which will be the best. So that sort of ensures that everyone had some ideas to contribute. Okay, so these are some of the strategies that can be done. And so you will design your instruments that did the students understand the process, did they understand the complete cycle, okay, and what is done in each cycle, and ultimately did they relate it, did they learn more, did they themselves understand, oh, I learned more by doing it. As far as the teacher is concerned, the key thing, if you are implementing, like for example in your undergraduate course when you'll be implementing, and Whitney would want to assess that you've done it correctly. First of all, she'll design certain instruments where it will be asked that you covered this thing, did you cover this thing, did you cover, how did you do it? Those different elements of the design. Did you give enough time to the students to do each element? Did you give enough time for them to redesign? Often, it's evidence is there in the scientific literature that you learn much, much more. Your learning enhances twofold or threefold more if you do get the redesign. opportunity. Okay, whatever you learn in design, really, it is enhanced and it's retained also. You can very easily recall it. Yeah. So that redesign cycle is very, very important, and also give an opportunity to the teacher to really document what worked and what did not work. So the evaluation instruments that will be designed as far as the teacher is concerned will be very different than as far as the students are concerned. Okay. Now, if we were talking about the thermal device, this is what we talked about. This will be one of the activity. Okay. So if we have done that thermal thing one, suppose my big idea was sustainability of energy, coming with sustainable energy systems. Okay. Then I could have had the essential how would the use of alternative energy sources impact my life as a person. Okay. How do I maximize or minimize energy transfer will be the challenge. Okay. Then how to design constructive device maximize energy transfer, and I would put the word thermal energy transfer here. Okay. This will be my guiding question. Then that will be my challenge. My guiding question will be design and construct a device that maximizes energy transfer and defend why you believe your solution is the best. So this will be the activity, and then this activity will be done for that. Okay. And of course you will, if this was a thermal energy device, then you go with content related to thermal, which you may have learned in your thermodynamics class. So this is what the key thing in the engineering design process is to touch all those points, to give enough time to do that. Of course, we had this activity most probably will be about a 50-minute type of an activity, at least the whole class. And next class, they will be doing reporting and all that. So it may run over 2 class periods, 2 days or something like that. Any questions? So this must not be very foreign to you all, because as engineering students, but it's amazing to see how the thinking is different. Okay. Whenever the word energy is used, more of a common person would think very differently than what you thought of energy related to forces. Because I think it's because engineers always look at devices where you're transferring force to do something, isn't it? And whereas the word, am I correct, Debbie? And the word energy would mean appear very differently.
Yes.
It is more to transfer heat energy or transfer thermal energy.
Or energy from one form to another.
Yes. So very, very different. But these were very interesting. These could be very easily done in a physics class. What you did. Huh?
You're so advanced. You don't came up with these.
Dominating middle school.
Yeah.
No, see, I use I removed the word thermal.
Good idea.
To see, I was just sort of a little puzzled in the beginning when I was seeing you all construct. What are you?
If you hadn't removed the word, because it would have each had fires going.
No, then I think I can bet with you each one of you would have used that font.
Yeah.
I can
I
guarantee.
thought for it once, but then
Huh?
I thought for it once, and then we did something with the sun, and the foil came to my mind, and
I can bet with you, you would have used the foil. Definitely. I did, you cut the foil and I thought about it, but then you started folding it. It's completely, but they were, both were looking at, more of one group was looking at a safety device. Okay, one was convert some type of, to gain mechanical work done through energy transfer. Okay, all right. So you were looking at a machine more or less to be able to do that. They could have used that for constructing pyramids. Because they had to
Seems awfully elaborate.
yes.
Pyramids
Do
are
like-
small.
Yeah, they got the pyramid construction down pretty well though.
Yeah, they have that figured out.
It was all physical labor.
They had
Well, those people didn't have any choice left.
Digital labor didn't-
Doing the donkey work more or
They
less.
had the, wait,
Okay, very good. Any, so if you don't have any questions?
I have a question regarding the unit creation. Like for each, like mathematics or science class, the teachers, they have a syllabus, right? They have to go to the 7th.
Which is just like your standard.
standard, just standard. So, but the 3 units which they are going to be integrated CBL and EDP, whatever the rest of the syllabus which is not covered, for which the units aren't being created.
Gradually, we want to create teachers who teach the complete syllabus using
Using this, yeah.
Okay. Actually, where people can construct the whole course. Last year, one of the faculty members who taught a course in, was it in geological science, whatever, earth sciences,
Yeah, earth
Yeah.
science, yeah.
constructed the
It's up
whole
to the teacher then,
course.
okay.
It was on the challenges,
Yeah.
earthquakes, okay, the whole course. And you know that his course material was used the most
Yes, it was.
by the teachers. Actually, one could, but it would be a very ambitious deal to do that. That a teacher can do when they become extremely efficient. But what I think is, for example, what you should do is, for the undergraduate class that you're doing it, you're basically teaching very well-defined chapters or sections. So you know exactly the content that has to be taught. Okay? So really, some of the guiding questions will straight away have to be, we need to learn this in order to solve the challenge. We learn to 1, 2, 3. What you have to basically do is think of a big idea and have a series. You could have more than one challenge related to the different content and each having some type of a design activity. Or you could do one. How long will your lesson be?
2 minutes.
I would,
2 55 minutes classes.
2 classes of 55 minutes each.
so I will do a really one challenge.
Is he talking about, are you talking
Are you talking about the year?
about?
No, I'm talking about the year.
Oh, I
Yes,
don't know.
I think it's like
2 weeks.
Okay.
For 2 weeks
I
also,
don't know.
yeah, but most probably it has to be 2 weeks. 10,
Okay.
yeah, 2.5 weeks, because 10 weeks of class, what do you have, 16 weeks, 15 weeks of classes? So it could be 3 weeks or something like that, okay? Think of not more than 2 challenges. If you can do with 1 challenge, that would be the best. Okay. Have a design activity where they use all the content that you have taught to use that content. So try to formulate the guiding questions such that those guiding questions address the content that you have to teach.
Is this in basic electric circuit?
Yeah, I'm talking about that.
But
Okay.
the 2 classes that we're going to be taking next week is going to be the same traditional way of teaching, right?
That I do not know what
I
it is.
think so, yeah.
Okay, so that the standard way of teaching, so that
Normal
you,
lecture.
yeah, so that you have the next baseline to compare with your experiences. But I'm talking about the fall semester class. So really, you have an ideal to develop 1 unit. Typically, a teacher's unit will be 2 weeks. Am I correct? Somewhat about
Yes.
2 weeks. If they do it very, very long, it could stretch too much. It can be over.
It's
You have,
usually a little over 2 weeks.
yeah. So theirs will be also
Yeah,
about the
like
same.
more than yours will be somewhat like that. do one, think of one unit, that whole thing, with one challenge related to a big idea, where there could be a lot of other challenges. Make the students really think that this challenge is only one of the possible things related to the big idea. There are a lot of others, so that they should get out of there thinking that they're only learning a certain part of the knowledge. There's much more to learn beyond this. Okay? That's very, very important, I think, for the students to get that idea. So I would design one unit which would be between 2 and 3 weeks long, with one engineering design project at the end. You can do small activities for each content, very small related activities. But start thinking when you do that, what guiding questions would you want your students to be asking, which are related to the content delivery and which are tied to your challenge. If you do that in advance, you may rethink how you organize the content. It could be different than the way it is in the book, the flow. So it could be done differently. Don't get completely brainwashed what is in the book. The important thing is you have to deliver that subject matter. Okay? Okay, very good.